And welcome back. As we go ahead and get ready to look at our next concept, which is that of polymorphism, we're going to first, though, start off with this idea of late binding. So, backing up just a half step here, we need to first kind of look at what are the key mechanisms of an object-oriented programming language. Well, when we look at most object-oriented programming languages, there's typically about three things that kind of really make it work, which are encapsulation, inheritance, and polymorphism. Now, polymorphism just simply refers to the ability to associate many meanings to one method name by means of a mechanism known as late binding, or sometimes it is referred to as dynamic binding. Now, the terms polymorphism and late binding are essentially just different words for the same concept. The term polymorphism is referring to the process of assigning multiple meanings to the same method name using, of course, late binding. Now, polymorphism and inheritance kind of go hand in hand. Inheritance allows you to define a base class and to define a behavior for that base class. That program can then be used not only for objects of the base class, but also for objects of any class that's been derived from that base class. Polymorphism comes into play by allowing us to make changes in the method definition for those derived classes and have those changes applied to the methods written in the base class. The way we've seen this is how we can kind of start overriding and overloading things very easily. We think about some of our different methods that we've already used and seen, for example, an hourly employee, salary employee, and how those kind of affect what we had created within our employee objects. Now, the thing is, we don't have to do anything special to use polymorphism because this all is happening automatically within inside of Java. But it's still important for us to kind of understand the process of how this actually works. And so to give us a better understanding, we're going to look at a little bit of an example. So when we talk about late binding, let's say we're designing software for a graphics package that includes several different kinds of geometric figures. Let's say rectangles, circles, ovals, so on and so forth. Now, each figure might be an object of a different class. So, for example, we might have a rectangle class, which has instance variables for height with maybe a center, so because maybe we're going to graph it. And a circle class might just have instance variables for like a center and a radius. Well, if we had a well-designed programming project that we put all this stuff into, all these classes could be descendants of a single parent class, let's say called figure. You could, of course, call it maybe shape or whatever you want, but it doesn't really matter here for our example. So, obviously, the first thing we want to do when we start thinking about is, well, if we're going to have a parent class, that means we need to have inheritance. So, let's apply some inheritance here. So, if we start thinking about how that inheritance comes to play, let's say we want a method to draw a figure on the screen. Well, to draw a circle, we would need different instructions from that what we need to draw a rectangle. All right, obviously, we still have something that establishes the screen, but how those get implemented is different. Therefore, each class needs to have a different method to draw its own kind of figure. However, because those methods belong to the classes, we could technically just call it draw. All right, we don't have to have a unique name for each class because, again, each class could use that draw method. So if, let's say, we have an object called R and it's a rectangle object and C is a circle object, we could say R.draw and C.draw, and these can both be methods implemented with different code. This is nothing new to us. We've seen this already before, but we're going to expand on this a little bit to really kind of give us that good, strong, foundational understanding of how and why this works. So this is where polymorphism starts coming into play with this example. So the parent class figure may have methods in it that apply to all figures. So for example, let's say we have a method called center that simply just moves a figure to the center of the screen, either by erasing it or redrawing it or whatever, however that is actually implemented with our code. But that method could be part of the figure class. Now, the method center might use the method draw, for example, to redraw the figure in the center of the screen. We may end up calling upon it because, maybe we want to make sure that when we draw this, it's a centered object because it's going to be easier to calculate how to do the other dimensions. When you think of using an inherited method center, for example, with figures of the classes, let's say rectangle and circle, you begin to see that there are some small complications. And that starts coming when we start extending this out to new classes. So let's just make the point a little bit more dramatic here. All right, we'll dial it up to 11. Let's just say we have the class figure that's already been written, all right, and it's in use in our code, and some later time down the road, we say, hey, we need a new class to come along, a brand new kind of figure. Let's just say we're going to add triangles into our program. Now, triangle could be derived of the class figure, so nothing new there. But the method center would be inherited from the class figure and thus should apply and perform technically correctly for all triangles. But here's where our complication comes in. The method center uses draw, and the method draw is different for each type of figure. Now, the method center was, of course, defined in the class figure, which means the method of center was compiled technically before we wrote the code for the method of draw for the class triangle. So that means when we start looking at how these methods play with polymorphism, if we invoke the method center with an object of class triangle, what we want is that code for the method center to use a method that wasn't even defined when we compiled the method center, namely the method draw of the class triangle. Well, can this happen in Java? Well, as we've already mentioned, yes, it can, because Java works things easily through polymorphism. It's automatic. We don't have to do anything special when we're defining a base class or a derived class in order to have polymorphism work. And that comes back to our topic of bindings. All right, we talked about late binding at the beginning, but there's other ones. And the reason why it works is because Java uses this mechanism known as late binding or dynamic binding. Binding, by definition, is a process of associating a method definition with a method invocation, so us calling that method. If the method definition is associated with the method invocation when the code is compiled, so when we just compile our code, we would call this early binding. However, if the method definition is associated with the invocation when the method is invoked or called at runtime, that is known as late binding or dynamic binding. What if we had used early binding, though, instead of late binding? Recall that the method center was defined in the class figure and that the definition of the method center included invocation of that method draw. Well, if for some reason, let's just say Java had used early binding instead of the late binding that we're familiar with, then when the code for the method center compiles, the invocation of the method draw would be bound to the currently available definition of draw, which is the one given within figure. Additionally, if we use early binding, the method center would behave the same for all derived classes for the class figure as it does for objects created using the class figure. Fortunately for us, because you might see, like, wait a minute, if it's got the figure definition, that's not going to work. Well, we don't have to worry about that because the way Java handles it, it says, hey, we're using late binding, so when center is invoked by an object of the class triangle, for example, the invocation of draw, which is inside the method center, is not bound to a definition of draw until the invocation has actually happened within our code. At this point, the runtime system knows, hey, this is a calling object of part triangle, and so it's going to use the definition given within the class triangle. It doesn't matter whether or not the invocation of draw is inside the method center or not. It's because, again, this is all happening at runtime. So the method center would behave differently for an object of the class triangle than it would for an object that's just a regular figure, because, again, it's two different objects. With late binding, as in Java or other programming languages that use a similar approach, things would automatically work out the way that you would normally expect them or want them to. So this late binding that we keep mentioning is a very important thing in Java because we want to have our objects know which definition that method is applying to. All right. So for example, when an object is created in a system with late binding, the description of the object must include whether it's either a direct description or an indirect, where the appropriate definition for each method is located. This kind of additional overhead that we have, a little bit of more work that we have to deal with, is kind of the penalty that we get for the convenience of late binding. But honestly, late binding is well worth it for especially languages like Java because of how you want them to work. It's like, hey, I don't want to necessarily be tied up in a definition before I'm ready to call it because what if things change?